video is a response to a question posed in a study group. The study group was connected with a MIT online course, and the actual course was, the professor was Professor Walter Lewin, and the course number was 802, and it was lecture 2. And the course is about electricity and magnetism. Lecture 2 is concerned with the field lines generated by electric charges. The actual question was, when you're dealing with a dipole, why do the field lines disappear at infinity as opposed to a monopole where they seem to go out to infinity? The answer is they don't disappear. They don't disappear either for a dipole or a monopole. They're shaped very different, and they fall off very quickly in the case of a dipole, but they're still there all the way out to infinity. To better understand this, let's look at an example here. So what's a dipole? Here we have an example of a dipole over here. Dipole is when you have two charges, a positive one and a negative one, separated by some distance. That gives rise to an E field, which is a sum of two constituent E fields. Go back over here, we have the same charge configuration, but we look at the constituent E fields. The positive charge gives rise to an E field pointing away from the positive charge. The negative charge gives rise to an E field pointing towards the negative charge. If you sum them up, you get this E field over here. So the first thing to note about the summed E field is that it's a lot smaller and it points in a different direction. It's pretty clear why it's smaller. If you add these two things up, adding vectors amounts to, let's say, adding the E minus to the E plus. If you wanted to do that in your mind, you'd say start here, add the E plus first, and then go up here and add the E minus vector to the tip of that, and that would bring you back down here. And the sum of the two would then be a vector starting here and going out to there, which is what we have over on this side. So you get a lot of canceling. A lot of the upness is canceled by the downness, and that's why you end up with a resulting E field pointing in the negative Y direction. Now contrast that down here with just a monopole, where the E field is always pointing away from the charge, or if it's a positive charge, and pointing towards it if it's a negative charge. So let's actually look at the E fields generated by the dipole and the monopole. To do that, I'm going to click on this little button. It takes a second for them for the program to generate them. But there they are. And now we can see why the E field is shaped the way it is, especially up in this region. The canceling of the up and downness over here gives rise to a horizontal vector. In any point along here, you're going to end up with a horizontal vector. And down here also, because of the canceling. Now, if you look over here, by way of contrast, this looks like the same sort of thing that's going on down here in the monopole case. Let me scale these a little bit so we can bring them both. They're pretty much, they're certainly pointing in the same direction. This one's smaller than that one, and you can see why it's smaller, because again you have canceling. You have one vector pointing in the positive direction, one pointing in the negative. You put them together, you're going to end up with something less than the both of them. So now, what about this idea of the vector field disappearing at infinity? Well, it doesn't. It looks like here that it's sort of gone, but if you go out further, these lines actually curve around, and you're going to hit more of the field lines as you go out. The field lines really tell you two things about the vector field. It tells you the direction, as we've seen here. It also tells you the intensity. How big is the electric field at the observation point, whatever point you're looking at. The field lines convey that information by the density of the field lines. If we go down here, ooh, the E field is very big there. Let me see if I can get it right in the middle again. The E field is very big there. In fact, it goes off the page. It's so big. And that's reflected in the field lines by being close together. They're very dense in this region. We go up here. Now the vector field is not so intense. It's very much diminished, and that's reflected in the fact that the field lines are further apart up here. So as you move away from the dipole, these two charges down here are actually called the dipole. As you move away, the field lines become more attenuated or thinned out. So it sort of looks like they're disappearing, but they're really not. No matter how far out you go, you're going to still find field lines. They won't be packed as densely, but they'll still be there. Now that those thoughts apply to the monopole also. Even though you see the lines going out to infinity, the field is definitely diminishing. The intensity is diminishing as you go out. Watch that. The vector here is representative of how strong the field is at each point. Back here, it's very strong. If I get close to the charge, it goes off the page. It's so strong. But if I go out here, it's diminishing in intensity. And that's reflected in these field lines, and that out here, the field lines are a lot further apart. Their denseness is a lot less, and that's because the field is less intense there. So up here, the denseness is, you can see it by looking at the difference between sort of horizontal lines. Over here, you have to kind of look at it via a circle. You have to look at what's going on and say a circle going around the charge at some given radius. So in conclusion, then, the field lines do go out to infinity. In fact, if we scale this thing up, let me generate different scale here and regenerate my lines, my E field. Takes a minute, and there they are. We have a field line out here at 20, which we couldn't see before because we were looking down in a little region here, and it looked like the field line sort of ended at the end of our observation box. But there are field lines out there, and in fact, we go way out here. This is going to eventually curve back, and we'll hit that field line. But they're very, very far apart, reflecting the fact that the field is extremely small out there.